Okay, Bismillahirrahmanirrahim. So, this will be our last lecture, and hopefully, this lecture number will be lecture 17. And after this lecture, I will also again upload another uh, video. Video that one will basically the solution of your final exam and the uh, second part of your second assignment. Okay. So before starting the class, just let me share the screen. Okay. So in our today's lecture, we actually go through the article number 8.9, superconductivity. So this time I will not follow the book because I will just try to follow the lecture note of good professors. So this will be the lecture note number 26. Okay. So superconductivity. So what is called superconductivity? Superconductivity is a phenomena in which the resistance of the material to be the electric current flow is zero. Okay. So there are two types of things. So that one is the perfect conductor, and the second one is the superconductor. So superconductor actually happens whenever we get uh, that means we get that material in some particular temperature. So we know that the resistance of a material basically depends on the temperature. So if we increase the temperature, then the resistivity increases. So if we decrease the temperature, then the resistivity will decrease. And at a certain temperature, this resistivity will become zero, and that one is known as superconductor. Okay. So these things was first discovered in 1911, whenever the scientists are working with the mercury, and they found that at 2.4 Kelvin, maybe the temperature is, yeah, sorry, 4.2 Kelvin, uh, they found that the material behaves like a superconductor. That means uh, a, there is no resistance to current flow. Okay. So superconductor is not relatable to the periodic table because superconductor is not such type of material that we can found in our periodic table, such as atomic number, atomic weight, or anything like that. In fact, the superconductor does not even the correlate with the normal conductivity. Okay, so superconducting compound may be formed from a non-conducting material also because we can also form this superconductor. Okay, using the temperature effect. So if you look at this figure, if you look closely this figure, then you found that for a normal metal, if in the x-axis that one is the resistivity, and in the in the y-axis that one is the resistivity, and the x-axis that one is the temperature. So for in normal metal, if you decrease the temperature after some temperature, its temperature will its resistance will be constant. But in case of superconductor, it has some critical temperature, which one is known as TC. Uh, that was the critical temperature. That in that temperature, these or those materials works as a superconductor. Here there is an example of lead. So silver, gold, and copper does not show conductivity at low temperature. Resistivity limit is the scattering and is limited by scattering and the crystal effects. Okay. Look, this one is an analysis of critical temperature, and for some materials, that one is actually experimented by the scientist for from the year 1900 to 2015. Okay. So there are different types of combinations are there, and for those combinations, the scientists here actually try to find out uh, the critical temperature of different combinations. Okay. Next one is the Mason's effect. The superconductor below this critical temperature expels all the magnetic field from the bulk of the samples. So that one is perfectly uh, diamagnetic substance, and this one is known as Masonry effect. Okay, so in that case, the value of psi m equals to minus 1. Okay. So if you look closely in this figure, that the superconductor with little or no magnetic field within a messenger state, that means uh, this whenever there is a superconductor inside that magnetic field, there will be no change in the magnetic field. But for a perfect conductor, there will be the change. Okay. Then next one will be the liberating magnet. So liberating magnet is the no magnetic field inside a superconductor liberates a magnet over a superconductor. That means there is another magnet or the behavior of a magnet that one is upon the superconductor. So this experiment is actually done by liquid nitrogen. So we know that the temperature of the liquid nitrogen is 77 Kelvin, and this one is very important that whenever some people are doing experiment, that means there are mm, say for example, if someone is would like to do the uh, characterization of a material, then he or she actually needs uh, this liquid nitrogen, because this liquid nitrogen is actually available, very easy to collect, and using the thermocouple, the people can actually use this liquid nitrogen for the low temperature, for calculating the low temperature effect. We can also use the electric oven for the high temperature calculations, but for the low temperature calculations, uh, this liquid nitrogen is actually very good options. Okay. So next one is the critical field versus temperature. So this one is the critical field. That one is and for the superconducting state, with respect, this one is shown that with respect to temperature, that one gradually decreases. This one is for lead, and there are few examples for mercury and tin. The curve, the pattern of the curve is same. Okay. Next one is the penetration depth. So there is a parameter, that one is the that one is known as penetration depth. So if the magnetic field Bx equals to B naught minus x divided by lambda, so this lambda is the penetration depth. So at the critical temperature, this penetration length is infinite, and any magnetic file penetrate the sample or the destroy the superconducting state. So near the absolute temperature, absolute zero of the temperature, our typical penetration depth is 10 to 100 nanometers. Okay. Now there are another two types of superconductors. Number one is type 1 superconductors, and number two is type 2 superconductors. So actually, type 1 superconductor is a single material, and type 2 superconductor is combination of different materials. So they have described about this type 2 sorry, type 1 superconductor, and after that there is a type 2 superconductor. This one is a combination of uh, two thing two critical magnetic field. That one is denoted by Bc1 and another one is Bc2. So if you look in this type 1 superconductor, then you will find only Bc, and in case of type 2 superconductor, you will find BC2. There are two types of two critical fields. Okay, so there are some examples of type 2 superconductors also. So and the effect of superconductors in high temperature. Okay, so the critical current density. So when the current density through the sample exceeds the critical value of Jc, that means the current density, it is found that the superconductivity disappears. Okay, so this critical current density Jc is very high for type 2 conductors. So here is a table for different types of material and its critical temperature, then the critical current density. Now the origin of the superconductor. So this one is actually discovered by three scientists. They are known as Burden, uh, Coopers, and Schaeffers. So this theory is known as BCS theory. So this one is not like the uh, Civil Service Examination of Bangladesh. So for low temperature, two oppositely spanning and the two oppositely traveling electrons can attract each other indirectly through the deformations of the crystal lattice of the positive metal ion. These indirect interactions at the sufficient low temperature is able to overcome the mutual Coulombic repulsions between the electrons and hence bind the two electrons to each other. These two electrons are called as Cooper pair. So this one is named based on this Cooper's name. Okay. There is a graph which one is actually shown from 19th century to 2000 up to 2015 based on the critical temperature and the BCS theory, and also the accurate theory is still challenging because this BCS theory is not uh, perfect. Okay, so this is all about from the lecture notes. And if I go there is an, go to the book, then I will show you there is an elaborations of this total thing. So you can also go through these things from the book. So first of all, this superconductivity. Then in the article number 8.9.1, zero resistance and the Mason's effect. So they have described how this superconductivity concept came. After that, they have described this curve. We have also described this one also. Then for different materials, the superconductivity concept. So that would professor's lecture note is basically the summarization of all these things. Okay. So you will find most of the things from here from this book, and you can also collect these things from the Wood professor's note also. So after that, the type 1 and type 2 superconductivity, and after that, you will find the critical current density. Okay. So try to solve the example number 8.8. Okay. Okay. And uh, the next one is the article number 8.10, the origin of superconductivity. I have discussed about the BCS theory also. Okay. So no need to go through the article number 8.10. So this will be the end of your syllabus and end of your last lecture. So I can also show you the syllabus. So our last syllabus was magnetic properties of the material, magnetic moment, magnetizations, relative permittivity, different types of magnetic materials, origin of the ferromagnetism, magnetic domain, soft and hard magnetic materials, ferrites. And we have already covered all these topics, and in these lectures I have completed the introduction to the superconductivity, zero resistance and Mason's effect, then type 1 and type 2 superconductors, and the last topic is critical current density. So hopefully this one will be the end of our syllabus. In the at the very end, I was very rushed, and in a very hurry, I try to complete the last chapter. So after this lecture, I will also upload another lecture. That one will be basically the list of assignment or list of the numerical problems that you need to solve for the second part of your second assignment. Okay. So hope for the best for the semester final exam and also for the Viva preparations. Okay. So thank you.